Okay, so now you should be able to see the PowerPoint and hear me. Is that correct? Good.
Yep.
So as I was saying, nonlinear thinking is different than linear thinking. And so we want to start looking at the ways in which they're different and what we can do about all of that. So this seminar series will try to help us think differently about situations, open up new ways of asking questions, new ways of looking at a situation. And the seminars are really going to focus not on how to do this stuff. In some sense, that's my job. All of you at the Institute, you can just have me do this. In other people, you may have to learn it at some point. But our focus here is really going to be on why you should care about these things, why you should think about thinking differently. We'll try to sort of take one approach to focus on in each seminar and work from there. As I said, the goal is really to get you new lenses to look through, because these types of new lenses can promote insights, can promote new questions, and probably even promote some funding. We'll schedule these things the first Friday of each month of the academic year. So that's September, October, November, et cetera. Today's an anomaly, being the second Friday of the month rather than the first Friday of the month. So we'll have next summer, if you're really interested about learning these things and how to, some week-long summer schools. If you want, you can bring your own data. We'll do sort of stuff based on introductory graduate statistics. So we're not assuming that you have much of a background at all. There'll be two sessions. One's going to be in May, and it's going to be focused on graduate students, predominantly the trauma track students, but other grad students as space allows. And then one for a general audience the week of, looks like July 11th. So a little bit about me. I'm a nonlinear physicist, and physicists, in case you didn't know, can be annoying. In fact, this tells us a lot about how we can be annoying, because we'll just kind of come in and tell you how to do what it is that you already are doing. We will oversimplify things, we will make some random comments, and we will generally look down on you. And the comics got it right. Liberal arts majors may be annoying sometimes, but there's nothing, absolutely nothing in this world more obnoxious than a physicist first encountering a new subject. I'm going to try to not be so annoying. And I apologize for advance in the times when I do get to be annoying. Physicists, however, are willing to analyze almost anything. I mean, we'll look anywhere for problems. And sure enough, we're less fussy about the problems we look at. We don't care what they're about. And we're also happy to borrow and steal ideas from everywhere. And I do mean from anywhere that's useful. What we do like to do is we like to focus on the questions and then make it up as we go along. A lot of times people are like, wait a minute, aren't you supposed to have it all laid out in advance? And the answer is no, you really never do. And if you think about it, nobody ever really does something once. You do it once, and then you figure out what's going on, and then you do it a second time, and that's the one you publish. And so it looks like you knew what you were doing all along, but you really didn't. So we're going to focus on questions, and we'll pull off methods as necessary. So let's look at this. This is a Sierpinski triangle. That's the name of this fancy thing. And how could you make something like that? If you want to unmute yourself and just tell me about it, or if you want to put something in the chat, you could say that. But how would you create a figure such as this? What would have to happen for you to make this figure? Anybody got any ideas as to how you would get to something like that?
You have to repeat things at different scales.
So Joe says we've got to repeat things at different scales. What precisely are you repeating? Can you be a little more specific about what seems to get repeated?
The shape of a triangle.
Okay, well, he says we've got this triangle, and notice if you think about it a little bit, maybe we could say we take that big triangle and make it black, and then we're going to take a white triangle that's half the size, invert it, and stick it on top. So we take out that middle piece, and then we've got 3 black triangles, and we take 3 white triangles out of that, and we repeat this over and over. So that's certainly one way to do it. So somebody said keep removing the middle third of the triangle of each triangle. Sure, right? That works out, and there's a nice sort of recursive approach to things. Okay. You absolutely would end up with a triangle that way. But it turns out that's not the only way we can get this thing. There are 2 common approaches to making something like Sierpinski triangle. One is this recursive deterministic thing, right? Joe just gave me a rule, and Joshua looked at something in the chat, just gave me a rule and said, look, you start with a triangle, you create a triangle, blah, 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 blah. But it turns out there's a relatively, almost completely random way to do it as well. Draw the vertices of the triangle, big triangle. and then pick a point anywhere else on your sheet and put a dot there. Now roll a 3-sided die. Okay, you don't have a 3-sided die. Roll a 6-sided die. 1 and 2 will point at point A, 2 and 3 will point, or 3 and 4 will point at point B, 4 and 5 and 6 will point at point C. Pick a point and go halfway from the point you have to wherever you rolled. Put a dot there. From that dot, roll the die again, go halfway. Repeat that previous step over and over again. Ignore the first couple of dots because the first couple of dots could have been anywhere. But it turns out you'll do this over and over. You'll exactly reproduce the Sierpinski triangle the way that this recursive strategy did it. Okay, there will be no difference in the outcomes. One is completely deterministic, one is completely random. Okay, but they both end up working. So which is the correct way to think about the Sierpinski triangle, the deterministic or the random? Which is more insightful? And why is it more insightful? So assuming that you have both the deterministic and the random, which one of those do you think is more helpful to you to understand how a Sierpinski triangle comes about? And again, unmute yourself, put something in the chat, whatever you think.
I think random would be better because it seems more intuitive that the way the universe and particularly life would develop in evolution would be likely based on random processes.
Okay, so Joe, being a good social scientist, likes the randomness. Are there other answers that people have?
I like the systematic.
Okay, and this is somebody who's kind of caught in the middle because that sounded like Carrie, right? Is that and
That's
Carrie's got a,
Heather.
oh, it's Heather. Okay,
Yeah.
so why do you like the systematic one?
I guess I feel like it's more ordered and more likely to turn out correctly. I could see trying that dot thing and I make one mistake and the whole thing's screwed up.
Yeah, and it turns out even if you make that mistake, you'll very quickly get back into the pattern. You'll just have an extra dot someplace. Okay, but it does turn out they show up exactly the same. But notice there's no sort of clear way to say, oh, this is the better way or that's the better way. We just know that something's going on. Okay, so let's think about this not in terms of a Sierpinski triangle, but in terms of something like resilience or any other of your favorite social science constructs. Which is the correct way to think about resilience? Should we think about resilience as being a deterministic thing where there's a pattern and it just happens? Or should we think about it as being the random of, oh yeah, we have these things and there's some random stuff and a pattern emerges from all that random stuff? Now, which is more insightful to you and why? And notice the complete absence of anybody saying too much of anything with this.
Well, I think
it's a hard question.
I think my answer would be at two levels. So the deterministic is important in the sense that we are interventionists and we're trying to arrange for resilience. But I do think that at a deeper level of how behavior is occurring, it is random. And I think that determinism is a form of randomness.
Right. Okay. And so notice there is this sort of desire to have one and the desire to have the other. And this duality, the fact that sometimes it seems random's the better way, sometimes it seems that the deterministic's the better way, is at the root of the tension between what we often call the nomothetic and the idiographic approaches to doing research. Right. In one sense, our nomothetic studies assume normality, that is a particular, and it turns out rare type of randomness. So fine, if you don't assume normality, pick your favorite distribution. Our idiographic studies sound a little bit more deterministic. Oh, this happens and then this happens and that makes this happen and we can intervene. Or maybe it's the other way around. Maybe the nomothetic is really the one that's a little bit deterministic. And what happens with people when you work with individuals seems to be a little bit more random. I'm not really sure which way it is. Okay. And I'm not sure that we need to have an answer as to which way it is. It's one of these cases where we have two complementary ways of looking at things and we need both of them. But for everything that you think about that is deterministic, there's almost always a random approach that generates the exact same results. And likewise, for everything that you think is random, there's almost always some sort of deterministic thing that happens. Okay. And this is, again, this is the root of this tension. And so we have to think about how do we get at something that will enable us to encompass both of these, to be able to see the random and see the deterministic all at once. So it turns out that the underlying dynamics are really what we want to look at in terms of creating both versions. And the recursive approach can be understood by looking at all the possible sequences of the stochastic version, the random version. And the random version can be understood by saying, oh, the dynamics are going halfway to some random point. And if you take all the possible different ways that you can go from one point to halfway to one of the edges, you'll end up with a Sierpinski triangle. If you look up the chaos game on Wikipedia, there's a decent, I think it goes too fast, but there's a color animation that gets at this a little bit. Regardless, the dynamics are what we have to start looking at. We have to step away from a little bit thinking about, oh, do we want a population study? Do we want to do case studies, things like that? We have to say, what do we do to get at the dynamics of the situation? And even when we're impacted by external randomness, events happen to us. What we really want to understand, it seems, is the internal dynamics of a system. Okay. Now, you all probably already know all this. Okay. In this case, I'm being either an annoying physicist, or I'm putting different words on something you already know, or I'm doing a little bit of both A and B. Okay. But notice we really want to think about the dynamics, not necessarily about the patterns being recursive or what emerges. We want to look at those dynamics that fall underneath things. So to look at dynamics, we're going to play a game. And it's a game that I stole from John Butner at University of Utah, who stole it from somebody else. And I've just put a link to a Google Sheet in the chat. And so if you would, you can go to the Google Sheet and you'll see something like this. And we're going to use this to play a game. So you should, for starters, you should put your name someplace in column 1, and you should answer the question in column B as to whether or not you are tall. And by tall, I'm going to give you the operational definition of if you're over 5'8", you're tall. Okay. So you can just put that stuff in there, and we'll give everybody a little bit of time to catch up to it. Okay, and so while you're doing that, let's explain the rules. We're going to have relatively simple rules. You can stand or you can sit. Okay, and we're not going to make everybody turn their cameras on and actually do it. We'll just record the data directly into the spreadsheet to make life a little easier on us. And so at each round, you can choose to stand or you can choose to sit, but you should make your choice based on a rule. So I'm going to ask you to think about a rule. So look at Barney and look at Joe and make your choice based on what they do. So for example, if both of them stand, I'll sit. Otherwise, I'll stand. My rule is going to be if Barney and Joe are doing the same thing, I'll sit. Otherwise, I'll stand. And what we'll do is we'll look, we'll evaluate, we'll go to the next round. Okay. So think about a rule. You're going to look at Barney and Joe's entry, and it's either going to say sit or stand. And you're going to decide then, based on what they do, I'm going to do something. Okay. We'll use the same rule all the way through. So pick whatever rule you think is appropriate for you. Joe, you want to start by sitting or standing?
Sitting.
Okay, so in my rule, so everybody should pick a starting, right? Sit, stand, all the way through. Okay, my rule again is if they're the same thing, I'll sit. If they're not the same thing, I'll stand. Okay, so it looks like everybody pretty much has a starting point. So if they're doing the same thing, I'll sit. Well, Joe and Barney are doing different things. So for the first round, I'm going to stand. Okay, so I'll put stand. Go ahead and fill in that first round. What are you doing based on what Joe and I are doing? And for your rule, Joe, you want to sit or stand this next time?
I'll stand, please.
Okay. Okay, it looks like we've got everybody. Okay, so now we'll go to the next round. I said if they're doing the same thing, I'm going to sit. So I'm sitting down. Joe, you're going to do what?
I'll sit.
Joe's sitting. And everybody else can fill in based on what was going on in round one. We can do round two. Okay. And now we do round three. I look at Joe and Joe's sitting, I'm sitting. Since we're both doing the same thing, I'm going to sit. And Joe, you are?
I'm going to sit too.
Okay. Again, now we go to round four. I'm seeing both Joe and Barney are sitting, so I'm going to continue to sit. Joe?
Okay. I'll stand this time.
Okay, and now we go to the next one. Since we're different, I'm standing. Joe is going to
I'll stand.
stand. Everybody can do what they want. Okay, I'm going to, since we're both standing, I will now sit. Joe?
I'll sit.
Okay, and since we're both sitting, I'm going to continue to sit. Joe?
I'll sit as well.
Okay. And we could do this ad infinitum, but we'll stop here. Since we're both sitting, I'll sit. Joe?
I'll sit too.
Okay. And so now we have some data which are not unlike data that you might take in any longitudinal study. Okay. You've got a bunch of things where you have different participants. You have some sort of potential covariate, right? Height could be a covariate. I don't know that height has anything to do with what anybody is doing, but it could. It's certainly a possible covariate. And then we have sequences of things. And notice if I ignore the first couple, so I'll ignore like the first two rounds in the starting. Notice we have this. We have somebody who tends to sit a whole lot. We have somebody who tends to sit a whole lot. And notice this is 2 sits, 2 stands. And notice we have a stand, sit, stand, and then they stay standing for a while. And then this is stand and sit. We have these different things going on. Okay. Some of them we see repeatedly. Some of them we don't. Okay. The question is, how would we like to analyze something like this? How would we go about deciding what's going on in terms of the dynamics? Because we could certainly do things like say, oh, what's the average number of people sitting and the average number of people standing, right? We could do population level studies. We could go back and we could talk to everybody and we say, okay, well, why did you do this? And Joe chose to do these things. What was determining whether or not you stood or sit, Joe?
I was not using a rule. I was just being whatever came in my mind, I did.
Okay, so Joe's dynamics were different than my dynamics and probably different than your dynamics because they were in some sense random. Right? They were not deterministic. And so this has some influence because you all looked at this. Okay, so you don't have to look at the details of this thing, but notice we had some things where we saw some patterns and we saw some things where that didn't seem to pattern and so on. So we updated the sheet, we did all these things. So if you didn't know the underlying rules, if you didn't know that we were playing some particular type of game, and you came in and you saw people standing and sitting, just like if you don't know the rules and you come in and you see people who score this on some PCL measure or this on CSE or whatever, how would you go about looking at this? How would you go about analyzing a data set that looks like this? Okay, so again, unmute yourself as necessary or put it in the chat. What would drive what you would look at and how you would start looking? What questions could you ask?
I guess there's sort of two things. So you have individuals. So you could look to see the extent to which individual standing at time 1, we'll say is, affects their standing at time 2. And since
Okay.
we kind of know a little bit that we were interacting with each other, you could also see if one individual standing at, say, time 4 affected other individual standing at time 4. So you could look at the extent to which, since I'm assuming these are people like embedded in a setting, right, in the classroom or something.
Right. So I
the
mean,
extent to
here
which
we're
yeah.
here we're embedded in a seminar. So
Right. Yeah. So I'm saying, like, if we saw this data, we have 8 observation points, but we also know that they're all embedded in the same environment.
right. Okay. And so we're looking at perhaps environmental issues, but we're looking at individual stuff. And Valerie puts in track, she'd look for trends, right? Look at the data. Why are they grouped in segments like this for a reason? Why, for example, do we have 7 people here and 3 people here and 2 people here with these nice breaks in between? So she's looking at a strictly environmental issue. Why is the grouping set up the way it is? She's not looking across this way. So notice we could look up and down the rows. We could look across the rows, or sorry, up and down the columns or across the rows. Both of those work out. Now, if it's completely deterministic, right? If we don't have someone like Joe here who's just sort of doing whatever he wants, if everybody was deterministic, it turns out we can very easily see what's going on, okay? We don't see it here because of the extra randomness that's put in. But we could look at those data, we'd see things. And what we would find are that there are particular patterns that we would see, right? We see, 2 sits, 2 stands, 2 sits, 2 stands, or stand, sit, stand, sit, stand, sit. Or perhaps somebody stands all the time, but they sit right here, right, for whatever reason. So here's a stand, 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 stand. And maybe this was just quote unquote noise is what we would probably think about this. It's like, wow, here's a really good pattern right across here. So Colin was standing the whole time, except there was some noise right there. Okay. And likewise, Steve, stand, 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 sit, stand, 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 stand. So maybe it's a new psychology professor thing that they chose to stand all the time and they just had this little sit right here. Okay. There are lots of ways we can go about making a sense of these quote unquote patterns or the attempt to make sense of these things. But it turns out that in a nonlinear way, we want to do something slightly different. Okay? And that is, we want to look for what are the possible patterns we could get, and then see which one of these we get and why and what we would do with that. So for example, we could do the following. So in terms of possible patterns, right, what we see here, we see things like lots of stand with an occasional sit. If you look really, really closely, right, and you have to look kind of closely to see it, is that after one of Joe's stands, I tend to change what I'm doing. So notice, when Joe stood up, I changed from standing to sitting the next time. When Joe stood up, I changed from sitting to standing. When Joe stood, I changed from standing to sitting. These are 2 different approaches to what's going on. This first one, lots of standing with the occasional sit, is a much more linear approach to things. It's what we normally do, right? We say we have some sort of average thing, we have some mean thing that works. However, what we see in this other one is that it's a dynamic situation, okay? So what you're going to have to do to make a change in mindset is to not think so much about these larger, population patterns or nomothetic patterns, or, why do we see these things? But look inside of what somebody's doing to say, can we suss out what's happening? Can we figure out, is there something going on where these dynamics depend on something else? Now, I did this fairly quickly because it's not my first day on the job doing this sort of thing. Part of what we want to accomplish, and maybe not by 11 o'clock Mountain today, but over time, is for you to start thinking in those ways too, so that you have that ability to look at the dynamics as well as look at all these outcomes. Okay, so it's not just we're going to throw all this other stuff out. looking across the columns or down the columns and saying, why do we have a 7-3-2 pattern? Or why do we have, Colin, Steve standing all the time, except they sit once here? Did something happen here that made them both sit? Was an airplane flying over and they got afraid, and so they count down. And I know neither of you are afraid of airplanes, but okay, we'll deal with it. We want to look at all those different things in a different light. We want to think about what's the dynamics internally, not necessarily externally, not the airplane flying over, but is there something in the more local environment, something in the interactions that's changing things? Because we could do this differently. Instead of this being Barney and Joe and Valerie and whoever else, these could, for example, be answers to questions on some sort of EMA, right? The ecological momentary assessment, where we're picking off things all at once, okay? And so we could say, how do these things, which are different questions or different moods or different perceived support, how do these things interact to produce these patterns? And how do they interact with each other so that one drives the other next time and then the other drives this one, okay? We want to look at making that change because that gets us a step closer to the dynamics. So let's stop for a moment and get any questions that we have. That have occurred to you, or anything that's not clear, or anything like that.
So Barney, this is, I don't know if this, I'm not sure I'm grasping enough to ask a good question.
Okay.
But, so there's dynamic processes happening within an individual. And then
Right.
dynamic process is happening across individuals, right? There could be an
Correct.
environmental thing which is influencing a lot of people, but it also could be that each individual has their own dynamic. That's not relevant to the current discussion, is it?
Well, I think it is relevant because you've separated sort of the dynamics within this group and the dynamics that come from outside. As I said, sort of semi-jokingly, the airplane flying overhead that made people sit all of a sudden. Because you look right here, there's a whole lot of sits compared to the stands. I mean, normally stand is not quite 50-50 on any given place, but here, all of a sudden, everybody seems to be sitting down right here. Right, and then now we've got a lot of people standing up after that. So maybe something happened in the environment, right? The plane flew overhead. Those are dynamics. And what you point to is actually a very interesting and very important thing of what constitutes the environment and what constitutes the inside sometimes. Sometimes we'll say that, oh, that thing's external to the system. Is it external? Is it internal? Is it one of these things that just sort of swoops in and happens and then leaves? And it seems random, or is it really part of the system? And that's not an easy question to answer. And I don't think anybody's got a good answer for that one. So your somewhat professed confusion there is actually probably indicates you're understanding exactly what's going on. Any others? Okay. So what we're trying to talk about, what we're trying to look at, is to identify sort of what are known as attractors in a system. What are those things that tend to be dynamics, that tend to see patterns that we see over and over again, okay? Now, hopefully that wasn't too bad, but it was also unrealistic. It was unrealistic because everyone processed the same sort of environmental factors. Your environment actually were Joe and Barney, right? That was exactly what was going on. However, that's not what normally happens. Normally, people are responding to all sorts of different things. So let's do something a little bit better. Let's open up the environment. And we're going to do the same game, except you don't have to pick Joe and Barney. You can pick any two people you want. So we'll go back to the same Google sheet. And I'll put, it's still in the chat for everybody. But down at the bottom, there's an expanded game. And so we can put names and stuff like that there. So everybody can put their names in. And we'll play the same game. Pick two people, one people, respond to them in some way, and go from there. So go ahead, put your names in. You don't have to answer the question again, although you can, because we can copy it from previous ones, and how you're going to start. And once you have your two people, then we'll go ahead and we'll play. Okay, so since we're not seeing more people coming in, that may be it. So go ahead and pick your two people, pick your rule, and we'll go ahead and do what we're going to do. So for round one, pick how you want to do it. Okay, now we can do round two. Round three. Round four. And round five. Round six. Round seven. And finally, round eight. And we'll not do the analysis right here. But if you were to look carefully, you would find that there are more patterns here than there were in the previous one. I remember in the previous one, we had a couple of very long, Steve and Colin with very long sets of sit or stand with just one. This time, notice there is a little bit of this, but instead of just being one different, there's two differences here. And instead of seeing some of these other long ones, we don't see these other long ones. We still see some that look similar, but not precisely. Okay. And so in this, we've actually got more realistic dynamics. They're still a far cry from what you'd get in a psychology study, but they're more realistic because instead of everybody just looking at Barney and Joe, people could look at anywhere they want. The environment is whatever you want out of this. Okay. And so here's the problem. When we do this, you get a much more complicated game. Turns out in the reduced game, if there's no noise, there's only 8 things that can happen because it turns out everybody's only looking at 2 people. In the expanded game, because you can look at so many more things, that is, your environment is so much more complicated. lots of things can happen. So if everybody who registered showed up, there would be more than 1 trillion patterns that we could look for. And if you want big numbers, 1 trillion is really not big numbers. You want big numbers, go look at some of the genome research. And so the moral is partly, if we want to start thinking about dynamics, pilot studies, laboratory experiments, simulations, things like that, where we can control the environment, can really help us focus on the dynamics. Okay. However, you still have this problem that Joe raised between environment and the person, environment and what's internal. And so in the end, the complexity of being in a real world, in vivo, it's unavoidable. But we still want to look at the dynamics. And when I say that some of this is unavoidable, we could look at covariates, right? We could try the covariates. I mean, for example, we could try tallness here, and it turns out the covariates aren't going to do anything. They're just going to find, you're going to find that the covariates are just a random starting point. Okay, so maybe all the tall people sit. That's where they start, but it turns out the dynamics will quickly wash that over. And so when you want to think about dynamics, you want to think about which is more important, the internal dynamics or the traits, these covariates that we often use to help people, make sense of the data. And the covariates work well only if the latter are more important. That is, only if the traits are more important than the dynamics. Both are probably necessary to understand things, but notice most of the studies that we read, people are looking at, what are the traits? What covariates work? We always want to go back to, oh, I found this. Now let me look at the covariates. Let me see if I can find predictors for this pattern or that pattern. And the way people do this a lot of times is you see various growth curves. And there are, it seems, 400 different ways people do growth curves. Growth mixture models, longitudinal growth curves, all these things. These are all really attempts to approximately determine the attractors. And that's the piece that people want to think about. When you think about those things, they're trying to say, hey, let's group these different patterns that we see together. And these are better than covariates sometimes, but they're still often surface comparisons. And so there are even more modern approaches. And these are particularly good for some of these EMA type data. There's Gimme and GVAR and 3 or 4 others that people have developed. Okay, and again, this is not a how-to. This is just to remind you that there are certain things that we can do. But the dynamics are really about these things that we'll talk about over time called attractors. And so first thing we want to do is find what are these attractor states? What are these sorts of patterns that recur? When you look at something like a longitudinal growth curve model, where you say, oh, some people go up and stay up, some people go up, down, up. And so those will be 2 different groupings. We're really trying to figure out what are the attractors? What are the sort of archetypes of things that happen? Okay, and so a lot of times we come up with archetypes based on our own experience. We don't do it mathematically. It's the same type of thing. There's a paper that Heather's working on with Chip and I that does transitions and attractors in a slightly more dynamical systems approach that I think actually works out better. That's part of the reason we're writing the paper. And again, you could try covariates to help you out, but they probably don't work here. You've always got to think about the traits and not about, or you've got to think about the traits, but you've got to think about the dynamics as well, and which matters most in your situation. Sometimes it is the trait that matters. Sometimes it's the dynamics. I mean, we hear a lot about, we see a lot about racial injustice. Well, race is a trait in some sense. It may be a socially constructed trait and all those things, but it's a trait. You show up in a classroom on the first day and you bring your race with you, okay? In that case, how you're treated in that classroom, unfortunately, is largely dependent upon that particular trait, okay? However, that's different sometimes in recovery from trauma, where we're trying to think about not, oh, because you were over 5'8" or under 5'8", you'll respond to trauma a particular way. That has nothing to do with the dynamics of the situation. So you want to think about traits or dynamics. And this is something that will be helpful sometimes. We always talk about traits as being out there and there's something that influences us, but I don't think it works that way. All systems and all dynamical systems, we don't just take in our environment. we metabolize our environment in the same way that you metabolize food. You don't just take it in, you break it down, you do something with it. Some people metabolize gluten just fine, some people don't metabolize it very well, and so on and so forth. But then the system also feeds back into the environment. And if you think about the game we just played, right, you were part of the environment and part of the system. And so it's not easy to make a distinction between those two. We like to do that all the time. We like to think it's nice and we have an environment over here, we have a system over here, but the two are completely and inextricably linked. And there's nothing that you can do about that. Sure, we can try, but it never works out that way. So the problem in the expanded game and the problem in any real experiment is there's just too much data. There's way too much data to start thinking about the dynamics. Really, it's too broad an environment. And hence things like laboratory studies or simulations, or even sometimes it's just the anecdotes of the gut feeling you have as a clinician or your gut feeling you have as a teacher or whatever. And so if you want to start to understand dynamical systems and to think in these nonlinear ways, you really need to start thinking small. And you want to get as small as you can possibly go. Joshua Epstein wrote a book and he said, it's not what you can put into your model that's important, it's what you can take out of it. You want to constantly minimize what's in it so that you can focus on the dynamics. In this way, the population versus the idiosyncratic, it goes away. Everything sort of starts with idiosyncratic. And then from that, we say, how can we generalize what generalizes up to the population? And if you think that the problems that you'll face as a social science researcher are bad, genomics researchers have even worse problems. Fortunately, there's this whole necessity is the mother of invention thing. They have approaches to sort things out. And being a physicist, I'm happy to steal things. We can steal those. And in fact, we do steal those sometimes. I want a quick aside here. Implicitly, there are some critiques of randomized controlled trials that dynamical systems shows up. If histories and dynamics is important, and they are, almost everything ends up being an N of 1. And yeah, we hope to cluster things together, but what do we cluster on and how do we know this? This does matter. We really don't have data as to whether randomized controlled trials work in general, but we assume they do, even though we have some good intuition to the contrary. So there's some limitations to RCTs that dynamical systems will start bringing about. You're going to want to be careful with these, especially when you talk to funders who think RCTs are sort of the be all and end all. Although there was a seminar last week that NIH put on where they're starting to get away from this. So there's some hope. But things are not as bad as this. They're in fact much worse. William Solis wrote a piece where he talked about something that many others have talked about, that in many cases, means are completely meaningless. And the example that he gives is to talk about the average human. And he says, the average human has 2 eyes and 2 ears and 1 testes. He says, and we never see anybody like that, ever. So sometimes means don't mean anything to us. Scott also talks about what we see in terms of coordinations. And this is a really good insight in how to start thinking about what was going on in those games. And what we think of as properties, whether somebody is recovered or somebody is under a lot of stress or somebody has, a lot of suicidal ideation. These characteristics or properties are really chimeras that result from the interaction of underlying and often unseen components. In the same way that the patterns that would show up in our game were really the result of interactions of something else going on, right? It was interactions of other streams with what we were thinking was important. Human locomotion is probably easier to conceptualize this with, right? You can recognize walking and skipping and jumping and crawling and all these other things. They're easily recognizable behaviors. They just combine the components, right? The quadriceps and the kneecaps and the ankles and those ankles in different ways. It's easier to conceptualize locomotion because the components are visible, unlike what we were seeing in our game and what you see in psychological studies. You can't always see the components. And lastly, this is the thing that shows up in the game. The components and the characteristics are mutually influential. That is, They influence one another and how those dynamics go. So we don't always have a clear way of saying, oh yeah, this one doesn't change and it impacts this. No, A changes B, which changes A. Okay? And that's something we also saw in this game. So we'll have a discussion here. We've got about 10, 12 minutes left. And answer questions, take comments, do whatever else needs to happen there. And see what we have. So questions, comments, corrections, deletions, additions.
So one thing I noticed about the game while you were presenting it, if two people each pick the other as one of their people, they're going to get deadlocked, aren't they?
They can. It depends upon their rule, right? If I say, I'm going to look at Andrew and I'm going to do the opposite of what Andrew does. Every time you stand, I'm going to sit. And if you chose the same rule, then every time I sit, you stand. And yes, we're going to get dead. We're either going to flip back and forth, or we're going to get entrained into doing just one thing. And so that's one of those attractors that we could see, right? We could have the attractor of, oh, yeah, I'm just seeing the same thing. The underlying dynamic is I'm doing exactly what Andrew does, and he's doing exactly what I do. And so we end up this way. So very much what you're talking about is identifying an attractor there in the system. And that's why if you think small rather than trying to understand the whole system, you may get someplace sooner. So good observation.
If people metabolize their environment, does this, I mean, it seems to me like this sort of means that all research has to be N of 1 research, because the processes of change are going to be different in each individual, or at least the combinations of variables are going to be different in each case.
Yeah, and that's exactly the problem. And I think part of the reason why people don't do a lot of dynamical systems research, because very quickly it becomes, oh, wait a minute, this is almost an N of 1. And eventually we're going to try to build back up, right? We're going to try to say, okay, we have all these N's of 1. How can we combine them? Is there some way in which we can start to combine them back? But one of the things that happens in research if we don't pay attention to N of 1 is this. When I was back in education and I would read stuff, I was like, oh, that was so cool. I'm going to bring it into my classroom. And it never worked in my classroom. I mean, anything I ever read in any physics education journal never worked in my classroom. And eventually I realized it's because, well, first of all, I have a completely different population in their study. They said it was random, but it wasn't really a population, right? It was not everybody. It was, a convenient sample that they randomized. But the other is, we shouldn't expect the outcomes to generalize, but are there dynamics that we can look at, like what Andrew identified? Are there things that we're like, oh yeah, we will see things like this and like this and like this, and those things can then generalize to our population is going to be clustered like this. But I think good dynamical systems research almost always starts with N of 1 stuff, and then how we move forward is the tricky piece.
Well, nobody's speaking, so I'll keep speaking. So this may be a strange comment, but I'm reading B.F. Skinner's book called Verbal Behavior. And so Skinner has identified, operant learning for how it is that human beings come to learn to use words and sentences. And the dynamics, the mechanisms are, he lays out in some fairly clear ways. The product of those mechanisms is so infinitely varied that you'd never really be able to predict anything in any individual situation. So I'm thinking that's example of what you're saying. So there are mechanisms or dynamics that are operating that could be discerned even in a world where prediction and control will always be impossible.
Yeah, absolutely. And notice that even though there is sort of an infinite variation possible, for the most part, everybody who grows up in the United States speaks roughly the same language. I mean, there's dialects from here to there, but we roughly speak the same language because we roughly have the same environment, we have the same goals, we have the same voice box and nasal cavity and all that sort of stuff, right? And like everybody walks in roughly the same way. Okay, I mean, we can tell your gait from Dave's gait, from Valerie's, from whatever. But because we all have, you know, the same sidewalk and the same gravity and the same knees and ankles and this, and we're about the same sizes and things. So there is an infinite number of things that could happen. But in the end, it turns out because we share enough things, there's a smaller number of things that do happen. And I'm not real familiar with Skinner, but in the operant conditioning, sure. Right? That was the whole point of let's take all these other things so that everybody has the same environment. And if everybody has the same environment and the same goals and the same components, they'll end up with about the same behaviors.
And by the way, I just want to say that what Skinner did was he simplified the environment, like you were just saying, by breaking it down to its bare essentials. And in that way, he was able to discern the systems, right?
Well,
And notice,
sorry, go ahead, Barney.
I was going to say, and notice, so, and everybody had the same goals too. Because I mean, that's, if you ever have that student who just doesn't have the goal of pleasing the teacher or getting the good grade, God, they're frustrating to work with.
Well, and I guess the other side, Joe, too, is that not only, as Barney was saying, that we kind of have some similarities, but also the same similar things tend to predict outcomes, right? So if we take that language example, someone's vocabulary, one of the strongest predictor is their parents' vocabulary, their parents' education, because that determines how many words they're exposed to and whether the parents read to them and all these other things. Like, so we know, like, even though it seems so infinite, like we can kind of figure out what are like the big things driving the outcomes too.
Notice that's in some sense, that's a little bit like Andrew's point that, so could things get sort of entrained with one another? And in this case, yes, the parents and the children get entrained with one another. And so that's why the parents are such a good predictor.
And I guess that was kind of my question too, because in our example, right, like we're, if you talk about, we're looking at the n of 1, but it's not just the n of 1 because everyone's in that game and that isn't a closed system and they're all interacting with each other and their behavior is being determined by the other people's behavior in the system. So we can't, but I mean, I guess that's the issue, is that when we're doing these kind of modeling, it's going to vary, right? How much that's the case for the folks that we're predicting, and the extent to which it's going to be important to look at those variables.
Yeah, and that's also right. That assumes that there's no environment. I mean, here, as you said, we had a very closed environment. It was only this. Nobody was watching anybody who wasn't part of this spreadsheet. But that's not true in learning language, right? Kids do learn language places other than their parents. Sometimes that's good, sometimes it's bad, but they do learn it other than their parents.
Steve has a question.
Yeah, go ahead.
You're
I can hear you, Steve.
I hit it twice, sorry. Thank you so much. Great presentation. Kind of mind expanding for sure. I was wondering if you could maybe say a little bit about sort of how we identify attractors. So it seems like, we're so used to, measuring kind of at the manifest level, but how does that kind of tie into maybe seeing underlying structures? Because it sounds like the extent to which you can really reduce, the better. Right. So if I'm giving 3 different measures, but then, we've got these other methodologies, factor analysis, et cetera, but like, are there ways within nonlinear dynamical systems research to kind of simultaneously pick up on some of those underlying structures? Oh, now I think you're muted, Bernie.
Okay, yes. The short answer to that one is yes. The slightly longer answer is that you should come next month and we'll talk about precisely some of the ways in which we can start to get at attractors. Because there are approaches that will start to get us there. Especially some of the genomic stuff is amazing because they deal with incredibly large data sets and still manage to find that, oh yeah, look, this gene seems to be doing something here. We don't have to go quite that far to do things, but there are ways that people are using sort of building off of things like the latent growth curve model and stuff like that to start saying, okay, these look like attractors. Now, how can we start expanding out from there? So the short answer is yes. The longer answer is either talk to me sometime or come next month and we'll talk about that.
I'll plan on it. Thanks.
Okay. So we have time if somebody has another comment or question they want to deal with, we can do that. Okay, then thank you everybody for showing up. I'll give you a chance to get to all your 1 o'clock, or I guess 1 o'clock my time, your 11 o'clock meetings, or 10 o'clock Joe, or whatever time zone you happen to be in.
Yeah.
And you all have a good weekend too. Okay.
Thanks, Barty. Really interesting.
Thank you, Barney.
Good. Bye-bye.